Over the past few lectures, we've talked about compressors and turbines, which are really integral components of chemical plants and various operations. And when we get to cycles, you'll see that both compressors and turbines will play a pretty key role in defining things like the system's level efficiency and defining the physical state of matter at various parts in the cycle. And so it's important for us to really understand how to solve those problems involving those components individually before then we try to integrate the solution of a single component into a broader system, which could be 4 or more unit operations. And I wanted to really provide a flow for how I think about solving turbine and compressor problems, and hopefully that helps you as we do that throughout the semester, whether it's immediate in homework or moving forward in exams or even past that into cycles. And when I'm confronted with a compressor or turbine problem, for me, the first step is to always solve the isentropic case. And of course, right, that's where delta S for our system is equal to 0. But before I do that, right, I ask myself a question. You know, is the fluid steam or another gas? And to me, the answer to that question is really important, because if it's steam, you know, we're fortunate enough that we have a pretty extensive catalog of physical properties for steam, right? And those are called the steam tables. And every time that we've had to solve for the isentropic case, we've essentially done the very similar things. So we have to, within the steam tables, we essentially have to interpolate for the final temperature and the final enthalpy at the final pressure, right? Given the initial conditions, right? So the initial entropy. And that's where the interpolation comes in. And hopefully, as you continue to solve example problems, you become more and more comfortable with the interpolation process, because that's going to be important. At some point, we're going to be double interpolating, where now the pressure lies between the two values in the steam table and the temperature is going to lie between the two values. So we'd really like to become comfortable with this single variable interpolation before we move forward into that. And then the second step when we're working with steam is that once we know the final temperature and enthalpy, then we end up really calculating the most important parameter, which is the change in the enthalpy when you have the isentropic condition. And that's done directly from the value that's interpolated from the steam tables. If it's not steam, if it's some other gas, well, instead of using the steam tables, we have equations that we've used. And the first step is that we've been finding the final temperature for the isentropic case from our entropy equation, where we know delta S over NR is equal to 0, which is equal to the integral from the initial temperature to the final temperature of Cp over R dt over T minus the natural log of the final pressure over the initial pressure. And often we design turbines and compressors based on pressure, and we know the initial temperature. So T2, maybe that's a better thing to do. I didn't use TF in that equation, but finding T2 using that equation is usually the first step in solving for the isentropic case. And then the second thing that we do is that we calculate delta H when delta S equals 0 from our normal equation, right? That delta H is just equal to the integral of Cp dt, or the integral of R from T1 to T2 of Cp over R dt, right? And the outcome of this first step in solving the isentropic case is finding the final temperature and then finding delta H when delta S is equal to 0. So now we typically have this, right? And problems around compressors and turbines then almost always have an efficiency component to them. So the second step in a process like this leads me to ask myself another question. So, it's, am I given the efficiency, or am I asked to find it? And you're going to follow two different pathways depending on which one. So if we think about this, if we're asked to find the efficiency, so we're going to call that case A. So this will be like 2A, is I'm asked to find the efficiency. Well, if that's the case, right, we really only have two variables. So we have the final temperature and the efficiency. So you can't be missing both of those when you're solving these problems. So if you're asked to find the efficiency, you'll notice that you're actually given the real final temperature, okay? And now we can solve this problem given either the steam tables or given the equations. So if we're given the real final temperature, right, and we're asked to find the efficiency, well, that actually means that what we're able to do, and we'll call this maybe like 2(1)A, right, is that we can just directly get the final enthalpy from the steam tables. Which allows us to directly calculate delta H real. And then once we do that, we have delta H when delta S is equal to 0, and we have delta H real. So then the second step there here, hold on. That was a silly, that's supposed to be A1A. Then the second step, if we're asked to find the efficiency, then of course, if we already have delta H real and when delta S is equal to 0, is we're going to calculate the efficiency, right? And we know that the efficiency of a turbine is equal to delta H real over delta H when delta S equals 0. And the efficiency of a compressor is equal to delta H when delta S equals 0 over delta H real, right? So we're going to use one of these equations, depending on if it's a turbine or a compressor, to calculate the efficiency. Now, if we have equations, right, instead of the steam tables, well, we'll call that maybe A1B is that we're going to use equations. And if we have the real final temperature, we actually can just calculate delta H real from the same equation that we have above, where delta H is Cp dt, right? But in this case, delta H real is equal to R times the integral from T1 to T2 real of Cp over R dt. And then from there, it's also very simple to do this, right? The next step would be to calculate the efficiency, given if it's either a turbine or a compressor problem. Okay, so that's the first part of the second question that I asked myself, is that am I given the efficiency or asked to find it? Now, if you're not asked to find the efficiency, but we're asked to find the final temperature, and remember, we only have two possible variables, right? The final temperature or the efficiency. And so this means if you're asked to find the final temperature, that you have to be given the efficiency, okay? And when that happens, we also have two pathways, depending on whether it's the steam tables or whether it's another gas. So if you're using the steam tables, really the first step, right, which we'll call B1A, is to find delta H real from one of the equations above. And here I'll write a star, but it's either from here or from there, because if you have the efficiency and you've already solved for the isentropic case, then solving for where the delta H real is possible. It's the only variable in one of those equations above. Now, if you're using the steam tables, this gives us an interesting challenge, because now we're actually going to use that to find the final enthalpy from, the final enthalpy is just the initial enthalpy plus delta H real. And then the final step here is then to interpolate the final temperature, T final, now that we know the final pressure and the final enthalpy. And doing this sequence of steps for the steam table problems will give you essentially all of the things that we could ask, right? Whether it's find the efficiency, find the final temperature, etc. Now, if we're not using steam, but we're interested in another gas, whether oxygen, CO2, hydrogen, something like that, well, we're going to be back to using equations. Now, this first step is actually identical to what you would do with the steam tables. If you're given the efficiency, go ahead and directly find delta H real from those equations above. But now finding the final temperature is much easier. It's just a single step. So B2, sorry, I kind of messed up my numbering system here, is we can directly calculate the final temperature, the real final temperature, from the same integral that we used above, except now we actually know delta H real, and that's equal to R times the integral from T1 to the real final temperature of Cp over R dt. And in that equation, the final temperature is the only unknown. So to just recap this, and hopefully it's very helpful to you guys, that I just asked myself two questions when solving compressor and turbine problems. The first, after is this steam or another gas? And then I solve the isentropic case, either using the steam tables or those two equations that you see on the right. And then once I've solved the isentropic case, I ask myself, am I given the efficiency or am I asked to find it? And whether I'm given the efficiency and asked to find the temperature, or the real work, or if I'm asked to find the real work and final temperature given the efficiency, I either follow A or B.